In the first lecture, starting from the basic premise of quantum mechanics, or I should say premises of quantum mechanics, we derived the Feynman path integral. That path integral is now going to be used to get to the concept of the instanton, and as you know, we have before us a big agenda, which I shall now put before you once again. So this being a short course on instanton physics, nevertheless, the amount of material we shall have to cover is substantial. Okay, so last time was the path integral. Today we do imaginary time and get to the concept of instantons after talking about a double well, that is to say a potential which has got two minima, symmetric in this case. Now for this I will need a basic tool which is called functional analysis, and this is a very well developed subject in mathematics, but we'll need only some rudimentary ideas over here. Okay, so you're very familiar with the idea of a function. A function is a machine that takes an input number and puts out an output number. So for example, if you put 2 and this is the squaring function, you get 4. Well, a functional takes as input a function, not a number, but a function, and it puts out a number which we shall call f of g. And f of g, for example, can be an integral over another function, that function being of, in this case, of x, the function g of x, the function g prime of x, and so forth. Okay, so for example, L could be the squaring function, A could be 0, B could be 2 pi, in which case this will be the number 0 to 2 pi integral dx cosine of x squared, and that, if I can calculate right, has the value of pi. Now let's come to derivatives. We know what a derivative is in the ordinary sense. Is the function at one value minus the function at a slightly different value divided by the difference of the arguments, which is epsilon, and then you take the limit epsilon goes to 0. Well, a functional derivative is similar but different. So to the functional, you add a small function. When I say a small function, this epsilon here is a number and we divide by that same number over here. But this functional derivative has got two arguments. It's got y and x. And we've added in a small perturbation, epsilon delta of x minus y. So in other words, this perturbation is non-zero only when x is close to y. And then we subtract it from the value when epsilon is 0. To give you an example, well, in the case of an ordinary function, the derivative of x squared is 2x. The functional derivative of f of g of x with respect to g of y will be f prime, which is 2 times this delta function. And you can see that very easily by simply squaring this over here, subtracting from here, ignoring epsilon squared, and of course the epsilons then cancel out from the top and the bottom. Now what is going to be very important for us is the analog of the Taylor expansion. The Taylor expansion for ordinary functions says that if I move a small distance delta x away from x, then at 0th order I get the function back. At first order, in delta x, I get delta x f prime of x. At second order, I get this, and so forth. And this is something that one is used to in ordinary calculus. Similarly, there's a Taylor expansion for functionals. So if I take a functional and I disturb it by adding delta g of x, well, then I get to 0th order this, to first order this. See, first order I'm saying because there's only one delta g over here, just like there's only one delta x over here. And then at second order, I get the second functional derivative, and then two of these delta g's. So in other words, in the case of a functional, we are allowed to expand about any given function. And of course, there's a lot of mathematical rigor that needs to be addressed in such things. But we physicists like to do things simply. We are functionally oriented, and I mean that as a pun. We'll shortly apply the idea of functionals, but let me remind you of what we did the last time. We said that if there's a point A and there's a particle located here at time ta, then the amplitude to go from A to B is then e to the is over h. This is the action divided by Planck's constant h bar, and then you sum over all paths. You get the Feynman path integral, which we got from ordinary quantum mechanics. We said there's this integral over all paths is then has over here a measure. That measure is a bunch of dxi, so dx1, dx2, all the way up till n minus 1, n goes to infinity. So in other words, we chop up the interval between a and b into n time intervals. And then we integrate over each time integral. Okay, then we got this formula with the action being this L of x dot, where the Lagrangian, and this is the Lagrangian, which is the kinetic energy minus the potential energy. And I remind you that there's no m over here because we've taken m equal to 1 for simplicity. Okay, now I also mentioned the last time that we are particularly interested in the semi-classical limit where this Planck's constant is imagined to go to 0. Now, of course, we can't. Planck's constant is given to us from maybe the time of the Big Bang. We can't do anything about it, but it's small, and we can always imagine that it's still smaller than what it is. And we're going to be doing the semi-classical approximation, which means that okay, we have already got one huge problem over here that since h bar is small, this thing over here is going to oscillate wildly. So how do we control this mathematically? Well, this is where imaginary time comes in. So let me put t equal to I tau and dx by dt squared. Well, you see, if t is equal to I tau, then dt is equal to I d tau, in which case this becomes minus dx by dt, minus dx by d tau squared. And this I'm going to call, so by definition, x dot squared. Okay, in the integral that we have for the action dt, well, if I put dt equal to I d tau from here, then I squared being minus 1, I get a minus over here, and this minus is going to be absolutely crucial. So we then have the amplitude as the path integral exponential of minus s of x over h bar. Now, two very important things to note over here. First of all, we've got a minus over here. Secondly, there's no minus here. In fact, this x dot squared term, we'll call this the kinetic term, and this is the potential term, they're adding up. And so both of these have the same sign. That's important to remember. This is what is called the Euclidean action. Now, in quantum mechanics, it's rather mysterious why you call this the Euclidean action, but in relativity, where you have a signature of the metric, well, then that means you put all the signatures equal to 1, in which case, okay, you will call this the Euclidean action. Anyway, it's just a nomenclature. Now let's get serious. So here's the point A, here's the point B. We will call XC the classical path from A to B. How are we going to determine the classical path? Here is, after all, this is just the classical path, but the Feynman path integral says that we've got to integrate over all possible paths. And so here is this path, and here's this path, and there are an infinite number of paths between A and B. The general path we will call X equal to X classical plus xi. And of course, they're all functions of the time. And I won't even call this the imaginary time because I have to repeat myself again and again. Tau, we shall henceforth just call the time. So the path as a function of time is the classical path plus variations around it, with the condition that the variations vanish at the endpoints. So you see over here that xi is 0 here, and xi is 0 here. And so this is the condition that we will have to enforce on xi. We can only take those xi's in which the particle is at A at the beginning time and is at B at the end time. Okay, so now let's expand S, that is the action, around the classical path in a functional Taylor series. We saw in our brief introduction to functional analysis that the action can be expanded at 0th order, that's the classical action. Then there's the action at the 1st order. So you remember I called this delta x then, but here delta x I have denoted by xi of tau. So this is the small deviation away from the classical path. Then this is the 2nd order. So there are 2 deviations, what we call delta x and delta x again. And you can check this by simply computing the functional derivatives and verifying that this is indeed what the expansion of the action about the classical path is. Okay, now, how is this classically path to be determined? Well, we shall require the 1st order deviation to vanish, and that then gives us the 2nd derivative of the position is equal to the derivative with respect to x of the potential. That is actually Newton's law. But it's Newton's law with a small difference. In ordinary time, you have the acceleration, mass into acceleration is equal to the force. Here you have the mass into the acceleration equal to minus the force. Huge, huge difference then, and this is going to make all the difference. So you see, this is good or bad, I don't know how you see it, but this is Newton's law written in standing it on its head. Okay, so the first order is gone, which means that the expansion then of the action is the action along the classical path plus deviations from the classical path, with this operator sandwich between xi here and xi here. And then we'll write this as S0 plus S2. S1 is missing because S1 equal to 0 was the condition that we used for determining the classical path, and the classical path will be determined by this. Okay, so this is for an arbitrary path, and second order is as far as we can go. Of course, you could ask, why not have xi cubed, xi fourth, xi fifth? The answer is we can't ever do those integrals. We can write down the expansion formally, but it won't be of any use. Okay, so as last time, we had calculated the amplitude of a particle to go from A to B as the integral of the action. And now instead of S, I'm going to put S0 plus S2. Again, remember there's no S1 because S1 determines the classical path. Now, in this dx, this path integral here, note that we are only integrating over fluctuations. We are not integrating over the classical path because the classical path has already been determined by Newton's law. Newton's law in its strange manifestation. And so therefore, this measure, dx, is the same as d xi. You remember that x was equal to x classical plus xi, and x classical is fixed. It's been fixed by Newton's law. And so dx is equal to d psi. Okay, which means that over here, instead of dx, I'm going to put d xi. But you see, the second order action here contains or could contain the classical path as well. And that makes sense because we are perturbing around the classical path. Okay. Now let's get some nice results from this. I'll call this the low-hanging fruit because you need to do so little work in order to get this result. Let me define this thing E. We can call E the energy because, it sounds nice. Besides, it's going to be conserved. So define E as minus the kinetic energy plus the potential energy. So now take d by d tau of this. Well, that means that this is 2 xc dot xc double dot, and the 2 here cancel. So we have this plus, now if I take d by d tau of v of xc, then by the chain rule, I get dv by dx into dx by d tau. And so that's v prime into dx by d tau. In other words, xc dot. Take xc dot common, and what do you have over here? Newton's law. If you have Newton's law over here, then this is equal to 0. And so energy in this sense is conserved. That is, as long as one is on the classical path, energy is conserved, but not away from it. And that actually makes sense because we do know that classically energy is always conserved, but quantum mechanically, if you go away, then you have the Heisenberg uncertainty principle, delta E, delta T is h bar, And so this is consistent with that. Okay. Now, x classical is fixed, which means that the classical action is fixed. And that means that the classical amplitude is fixed as well. See, here is the amplitude which I had written from A to B. This had the classical amplitude, and this was the quantum stuff over here. So we know the classical stuff. On the other hand, now this over here is going to be more complicated, but it will be simple, or I should say relatively simple, if this S2 did not depend upon the classical path. And that is possible. I'll give you two examples of that where it does not depend on the classical path, in which case one can do this functional integral without worrying about the classical path at all. We'll come to that in a bit. Okay, so if this is independent of xc, then this thing over here is just going to be some normalization constant. And actually, we'll be able to figure out what that normalization constant is. Let me summarize what we've achieved so far. So the total action, and when I say total, we don't ever go beyond the second order action. The first order is 0. I keep saying that again and again. So there's the classical action, and there's the fluctuation part, and the amplitude is the classical amplitude times the fluctuation part, where the classical action is this and the fluctuation part is this, and all seems very good. So let's work out the simplest cases. See, always one must start out with what one knows, what one can do, and then slowly build up to the real problem itself. Okay? So what could be simpler than a free particle? I think there is something simpler, which is have no particle, but then the whole thing doesn't make sense. So let's start with one free particle, which at time 0 is at position x, at time t is at position x prime. And what we would like to do is calculate the amplitude to go from here to here. Okay, so here is Newton's law. It's Newton's law because that's the second derivative of the position, and that's equal to v prime, but v prime is 0 if v is 0. I think every child can solve this equation. It's x is just a straight line. Some constant times tau plus some other constant. Just differentiate this and you get 0. Of course, you have to have the correct boundary conditions, so you fix C and D. When the time is 0, tau is 0, then this goes away, xc is x. When t is tau, then x becomes x prime. And so this satisfies the boundary conditions. Okay, good. So I can calculate the action for a free particle. It's the kinetic energy plus the potential energy. There's no potential. And just stick this in over here, do the integral, and it's x prime minus x squared over 2t. All right. Okay, so now the amplitude to go from here to here is just e to the minus 1 over h bar into this. And so we've got the classical amplitude. Repeat now for the simple harmonic oscillator. Okay, so for the simple harmonic oscillator, we'll use the same boundary condition. Start at x0, end at x prime t. Okay. If you take the derivative of the potential over here, that's omega squared x. So we need to solve this equation, and anyone can solve this equation. It's just a linear combination of two functions, e to the omega t and e to the minus omega t. And then we fix c and d using the boundary conditions that at t equal to 0, tau equal to 0, I keep saying t, but it's the same thing, that the particle is here and then is here, so we have these two conditions, these fix c and d, and I'm not going to do the algebra because you'll get bored with it. Just fix c and d this way and calculate the action. And it's just a little bit of algebra, and you can actually do this in 5 minutes. The answer is that the transition probability to go from A to B is exponential of this thing. So this over here is the action divided by h bar. Let's see, can we make sense of this? Does it agree with the free particle? Well, the free particle, to get the free particle, we should let omega go to 0. If I make omega small, then sine or sinh or whatever hyperbolic sine of omega t, that goes to half omega t. And no, it goes to omega t. And in that case, we have this factor becoming just 1 over t. And look over here, cosh becomes 1. So this is x prime squared plus x squared minus 2x prime x, which is x prime minus x squared. So the free particle and the simple harmonic oscillator, they agree in the limit that omega goes to 0, as they should, of course. All right, now let me come back to the imaginary time integral, to the fluctuation integral rather, and we want to know how to compute this. Okay, so we expand xi of tau in some orthonormal basis, and I can always choose that orthonormal basis to be the eigenfunctions of this operator. So you see, this is by choice. I don't have to do it, but it makes things possible, makes it possible to go on with the analysis. So phi is an eigenfunction of this operator obeying the correct boundary conditions. That is to say, at the initial point and at the final point, these functions are zeros. Okay, so that says that x, which was xc plus xi, has been expanded this way. Now, I'll ask you to do a little calculation in your head. So in place of this xi, we are going to be putting this thing here and this thing here, these being orthonormal to each other. We can do the integral, and this will, so remember that this acting on phi n will give us lambda n, so that lambda n will come here. And so very easily, almost trivially, we get the second order action in terms of the eigenvalues over here and the square of Cn. What are Cn? Cn's are the coefficients of the orthonormal functions. Okay, so now we need to do this functional integral. And remember that this d xi came about because d xi and dx were the same, and Feynman told us we have to integrate over all possible paths. Well, so if I integrate over all deviations, that means I have to integrate over all coefficients, Cn over here. And I can always put a normalization constant like this over here. There's no problem about that. That simply redefines what Cn is. It's, I could have put it over here equally, but it doesn't make a difference. Integrating over all paths is the same as integrating over all values of the coefficient Cn. Because remember that the phi n's are supposed to be a complete set. If you take all possible values of Cn, you make all linear combinations of them, you're going to get to any function that is smooth, of course. Okay, so then our functional integral then gets reduced into an integral over the Cn's. How many Cn's are there? An infinite number of them, because this operator has an infinite number of eigenvalues. Okay, so then what I have is a product of 1 over the square root of the eigenvalue. And it's an infinite product. It goes from 0, 1, 2, 3, all the way up till infinity. And this over here is the normalization constant carried forward. And now you remember that a determinant of a matrix which is diagonal is just the product of the diagonal entries. So this thing over here is what you call the determinant. So this product, 1 over square root of lambda n, all these multiplied together, is exactly 1 over the square root of the determinant of something. What is that something? This operator. So many of you, for the first time in your lives, will be seeing not the determinant of an ordinary matrix, but of an infinite matrix. An infinite matrix, when diagonalized, has an infinite number of eigenvalues along its diagonal. When you multiply all of them, that is the functional determinant. All right, so this is our big result. That the amplitude to go from A to B is the classical amplitude, and then there's the fluctuation part. I wish life was simple. I wish this was the end of the story. But the problem is that it could be, doesn't have to be, but it could be, that one of these eigenvalues is 0. Then we're dividing by 0. And that means something terrible is happening. And what could be even worse is that this could be negative. And that's even more than terrible. So we will have to deal with very bad things in the future. But for now, let's be happy with what we've done and work out these infinite determinants for the situations that we can. Where we cannot, we will have to do a lot of thinking. But for now, with only a little bit of thinking, we can get this. Okay, so let me work out the fluctuation part for the free particle. Free particle is, potential is 0. Boundary conditions, you all know, we start from here, we end over here. The eigenvalue problem is very simple because this v is 0, so v double prime, the second derivative of v is 0. And so with this condition that there is no deviation at the beginning, no deviation at the end, then every child can solve this problem. Minus d to d tau squared is equal to lambda and phi n. And that's this thing. Just differentiate this twice. Okay? So this doesn't matter. This is the normalization constant. This normalization constant is because we want integral minus t by 2 to plus t by 2 or 0 to t of the square of this equal to 1. But to come back to this, differentiate this twice, put it in here, and you will get lambda n times this, where lambda n is this, n squared pi squared over t squared. Very, very simple. Okay. So then we know the lambda n's. There's no lambda 0 over here, because if we put n equal to 0 here, this function vanishes. So fortunately, by good luck, nature has gifted us this situation where we don't have a 0 eigenvalue. We have only eigenvalues from 1 to infinity. And so we have the fluctuation functional integral as the product of 1 over n. So it's 1 over n, 1 over 1 into 1 over 2 into 1 over 3 into 1 over 4, etc., all the way up till infinity. But again, life is not so simple, because you remember I told you the last time this n prime is infinite. On the other hand, if you multiply all numbers 1 over 1, 1 over 2, 1 over 3, 1 over 4, and you keep going, those numbers at the end keep getting smaller and smaller, so the product is 0. So this is 0, this is infinity, and this looks like total mathematical nonsense. Okay, how do you make sense out of nonsense? The way is, there's some solid knowledge we have, which is that at the very beginning we calculated what this normalization factor was for a free particle, and so infinity into 0 is equal to this. And when I say infinity, I don't really mean infinity, and I don't really mean 0, because we can always stop short of infinity. That's in our control. But this is very, very large. This is very, very small. Their product, we know, is this. So that is what will enable us to make sense out of nonsense. Okay, now I'm going to use the same approach for the simple harmonic oscillator, where this potential is this half x squared, omega squared x squared. You differentiate this twice with respect to x, you get omega squared. And of course, the boundary conditions are as before, x0 to x prime t. Your eigenvalue problem now is, this is v double prime. You have to solve this eigenvalue problem with the same boundary conditions, and even children can do this. So they know the eigenvalues. They're the same as before, exactly the same as before as for the free particle. However, the eigenvalues are a little bit different. So earlier we just had this for a free particle. Now we have omega squared. Well, pull this out and we get this. Okay, so now for the simple harmonic oscillator, the fluctuation thing looks very much the same as for a free particle, except that this now is a little bit different. And let's write this as two parts. So this part is what you saw maybe 3 minutes ago for the free particle. And now you are seeing something that depends upon omega. By the way, you notice that if I put omega equal to 0, this becomes 0, and this whole factor becomes 1, and that becomes the free particle again. Okay, now what do I do with this? Well, then you remember the courses that you took on in calculus, or if you didn't take them, then you can always go to Mathematica and you can ask, what is this thing? Well, this, we know. This thing is the simple harmonic, the free particle answer. What is this? Then you look up the tables, go to Mathematica, work it out yourself. By the way, this was worked out by Euler some 200 years ago. I don't know. But this infinite product then is in terms of hyperbolic sine in this way, standard stuff. And just multiply them together, you get the fluctuation amplitude for the harmonic oscillator. Okay. Now, notice over here, again, as omega goes to 0, this becomes, over here, just 1 over 2 pi h bar. And this is what we had here. Exactly the same. No surprises there. So we have found the amplitude to go from x0 to x prime t. I'd call this the script A earlier. There's another notation. This is called the Green's function. The Green's function to go from here to here, which is basically this. And you'll say, why take so much trouble? What do we gain by calculating the Green's function? We've done this for the free particle. We've done this for the simple harmonic oscillator. I'm going to tell you what we gain. So let's take a complete set of eigenstates of the Hamiltonian operator. Call them n. This is the eigenvalue equation for that. These are known to form a complete set. That completeness is here. This 1 is a unit operator. Notice the hat on top. So now I'll ask you to look at this. This is the same expression as above. And now I'm going to put a unit operator here. Why? Because I want to. Nobody can stop me from putting 1 anywhere. Well, if I do that, then this n and this x over here will give me the wave function at x prime, phi n of x. And this over here, see, h acts upon n and gives me en, which means that this Green's function is actually this. What is that? This is a sum over n. So there's E0, phi 0 star, etc., etc. The next one will be n equals 1, and so forth. Okay, now E0 is always less than E1. E1 is less than E2, etc. The higher you go in n, the greater the energies become, which gives me an idea. The idea is, let t become very large. Now the exponential goes to 0 very, very fast, which means all these terms over here will become negligible, and only the ground state will survive. That means that if I look at the limit of the Green's function as t goes to infinity, then I should be able to pick out all of these terms over here. In fact, let me do that. So let's see how I can convince you. In the limit that t goes to infinity, hyperbolic sine becomes e to the omega t. Move it up, it becomes and there's a square root sign, it becomes e to the minus half omega t. This factor over here, then I move here and here. So omega over pi h bar square root, I split it into 2. This depends upon x prime squared only. Now notice that as t goes to infinity, this becomes much, much larger than this, so I can forget this. And so what I have is the simple harmonic oscillator wave function for the ground state, which is this. And half omega t is the energy of the simple harmonic oscillator ground state. So something very nice has happened. So all the trouble that we took in order to calculate this quantity over here now enables us to get all the energies and all the wave functions of the simple harmonic oscillator without ever solving the Schrodinger equation. See, in our childhood, we used to solve the Schrodinger equation and get all the eigenvalues and all the eigenfunctions. But with the Green's function method, calculating the Green function is easy. And it's just the classical part multiplied by the fluctuation part. And there's nothing after that because there are no higher terms in the harmonic oscillator. So this is the easy way of getting the harmonic oscillator wave function. Of course, this is a trivial application of that, but and it's just to demonstrate the consistency, the importance of knowing the Green's function. Now I move to a different topic, the double well. So here I have two vacua. This is the lowest energy state here, lowest energy state here. They're degenerate. If there's a particle which is confined over here, well, it'll have some energy and it'll be bouncing back and forth, assuming it doesn't have energy to go over the hill. So it'll be just bouncing back and forth. Its wave function will be concentrated here. On the other hand, if there's a particle located at the right minimum, it'll be confined to this minimum around over here. Now, notice that the previous and this, they were not eigenstates of the Hamiltonian because the Hamiltonian has got definite parity. And this is obviously, I mean, if I make x go to minus x, this doesn't, this will just stay, it will not be plus or minus itself. Here is an eigenstate of the Hamiltonian. It's a symmetric one. So if I exchange the left and the right, nothing changes. On the other hand, here, if I exchange the left and the right, then the sign changes. You see that this would come here, this would go there. And so these two are the symmetric and anti-symmetric eigenstates of the Hamiltonian. That Hamiltonian, which has got a potential which is symmetric and has two minima, two symmetric minima. Now, I don't want to go into a too extended discussion, but suppose you were to solve this numerically, the Schrodinger equation numerically, what would you find? Okay, so you would find a symmetric state and an anti-symmetric state, 1 and 2 respectively, and they'd be very close to each other. Why? Because if you go back here, this particle and this particle are in identical potentials. Now, here is the symmetric eigenstate. Here's the anti-symmetric. Now, the anti-symmetric has got a node. That is to say, it has to cross zero somewhere over here. Because it has to cross, it has to have a little bit more energy than the symmetric eigenstate. And so we expect n equal to 2 to be slightly higher than n equal to 1. Finding this energy difference between the second and the first eigenstate is a major, major problem, and it cannot be done in perturbation theory. But we will do it here. Okay, so now let me come to imaginary time and double well instantons, and this is going to be purely classical at the beginning. So here's v of x, here's minus v of x. See, there is a particle which was confined to this position over here, or confined to this position over here. Normally, it wouldn't be able to go from here to here, but of course, we know through tunneling it can possibly do that. Suppose you were to put this particle at the top over here. Then, now what is this top? This is v of x, this is minus v of x. So what is a minimum has become a maximum. From the maximum, it will roll down. Now I remind you of what we had derived earlier. This is Newton's law. This is the conservation of energy, just what we had seen a little bit earlier. This tells you that the potential is symmetric. So v of x and minus x are the same. Let's look over here at the solutions of this equation of Newton's law. One solution is that you place the particle here with zero energy, and the zero of energy is just the top of this of these two peaks. So the total energy is zero. If we look far back in the past, that is to say at minus t by 2, or look far into the future, it is over here, it stays over there, and it never moves from there. Okay, so very boring, very dull. It does nothing. That's the stay-at-home solution. And of course, the amplitude for that is e to the minus the action. The action is 0, so the amplitude for that is 1. Let me look at now the other possibility. So it starts from here and goes here and then goes up. It starts from minus a and ends at plus a. So xc at minus t over 2 is minus a, and xc at plus t over 2 is plus a. And we always keep in mind that t is a big number. So after a long time, this is going to go from one peak to the other peak. Okay, now let's see what are the possibilities. Okay. Now, the classic, if you can see from here that if I make t go to minus t, this equation does not change. And so xc of minus t is minus xc of, I'll prove this on the next slide. That says that, so if I put t equal to 0, then something is equal to minus itself, which means that xc of 0 is equal to 0. Secondly, that if e is 0, so e is 0, then that says that xc dot is equal to square root of 2x v of x near x equal to 0. And so what that says is that the picture looks like this. Far in the past, the particle is at minus a. Far in the future, the particle is at plus a. Here, xc dot, here x is equal to 0. So you see that at t equal to 0, here x is 0. I should have put a c over here. I missed that out. But you see that it's there all the time, and here it's there all the time. It's only very, very close to here that xc suddenly jumps from minus a to plus a. This is what is called an instanton. This is the center of the instanton, and it happens very, very suddenly that it goes from minus a to plus a. Why? Why do I say suddenly? Because most of the time it's here. It's only here that xc dot becomes non-zero. You see that the slope over here, xc dot, is big. And now, instead of talking generally, let me take this specific potential. V of x is equal to this. Okay. When I invert it, it's that. You've seen all these equations. Here, I've taken the derivative of v. V prime is equal to this. So you can see that when x is equal to plus or minus a, this is equal to 0. So the derivative is 0 over here and is 0 over here. The solution of this equation, Newton's law, is this. This is what is called an instanton. We have an explicit solution for it. Xc, x classical. So this is the solution of the classical equation of motion, in other words, Newton's law, and it's a tan omega t over 2. It obviously obeys the right boundary conditions because at minus infinity, you have x. See, tan goes to minus 1. Hyperbolic tan goes to minus 1. At argument minus infinity, hyperbolic tan goes to plus 1 at argument plus infinity. So we have minus a and plus a. Let's check if this is indeed the solution. So let me take two derivatives, like over here. So I take two derivatives, and you'll have to believe me or just do the calculation yourself. Very, very simple. This is what it is. Then use the identity that this over here is equal to Sheck squared. And you get this. But you recognize that this over here is the same thing. And so the solution is indeed correct. So I've given myself a good mark. Correct. Now, you can see from this omega tau over 2, when this becomes of order 1, then it approaches the asymptotic big or asymptotic small. And so this width over here becomes order 1 over omega. If I make omega big, that width becomes small. And in fact, if I make omega big enough, then this becomes a kink. A kink which is the limit of something that goes from below to above, and it does so very, very fast. Well, that's what we call a kink. I should have put this earlier, but that's okay. Here's the proof that for this potential v of minus x is equal to v of plus x, that When I reverse time and put a minus, that also is a solution. So in fact, we have not only the instanton, we also have the anti-instanton. The anti-instanton moves backward in time. So if I was to put t, okay, see what happens over here. If I put t going to minus t, then the hyperbolic tan becomes this. Suppose I go to minus t equals infinity, then this becomes plus a, and then plus a goes to minus a as t increases. So that's the instanton. The other remarkable thing is that it doesn't matter. You see, we don't know when the solution will cross zero, because here, if I put instead of t or tau minus something, any constant, nothing changes because this dt squared is invariant. Which means that if I take this, well, this is an equally good solution of the equations of motion. And so we can have not one instanton, but we can have two instantons, 500 instantons, and an infinite number of instantons moving between minus t over 2 and plus t over 2, provided t is large enough. So now, just to give you a picture of that, so this is one instanton. It almost looks like a kink. Here I have three instantons. So you see, here I went from minus a rapidly to plus a. Here I went from minus a to plus a, stayed there for a while, came back, stayed at minus a, went up to plus a. So how many times did I cross? Once over here, 1, 2, 3 over here, and here 1, 2, 3, 4, 5. One instanton, two instantons, 5 instantons. When I say instantons, I mean I include the anti-instantons as well. The instanton action, you saw this earlier. It's this. Energy conservation, you also saw. We had chosen the total energy to be 0. So from here, we can calculate the instanton action. But you see, instead of having to go from minus infinity to plus infinity, because the instanton is very, very short-lived, we can go from a little bit to the left and a little bit to the right. I mean, a little bit to the left of where the instanton crosses the axis. So in this very short time interval, minus delta to plus delta, that's the only integral that we need to do. And the derivative is non-zero only where the instanton is located. If it is located at x, then the derivative is big around x equals 0. If it's located at 1, x equals 1, then it's big around x equals 1, and so forth. And of course, we can immediately write this xc dot squared as this, which is this. So that's actually quite trivial. For the special case that we looked at for the double well, the action is very easy to calculate. It's just 2/3 omega a squared. If you have n instantons, now let me tell you about n instantons. If they don't know about each other, then the total action is just the sum of the actions. If they overlap with each other, then nobody can solve that problem. So in fact, the only way that people have managed to deal with instantons is deal with it when it's a dilute gas. What's a gas of instantons? It's like a gas of ideal atoms. Ideal atoms don't interact with each other. We learned that in basic physics, right? That an ideal gas has got atoms which are so small that they don't ever touch with each other or interact with each other. In the case of instantons, those instantons are so localized that they never feel other instantons because they're so far separated from each other. Okay, so now the other thing is that this instanton center can be located anywhere between minus t over 2 and plus t over 2. So we must sum over all possible values of the instanton's position. How many are there? An infinite number of them. But another way of saying that is that there are t of them. So this integral over here has to be done, gives you t. Okay, so just one important thing before we conclude this. If the first instanton crosses the axis at tau 1, then the second one has to do so later. The third one has to do so later as well. So if I am to do the integral over t or tau, then of course this tau 1 must go all the way from minus t over 2 to plus t over 2. On the other hand, tau 2 has to come after tau 1. In other words, tau 2 has to be bigger than tau 1. So this integral must go from tau 1 to t over 2. The one from the integral over tau 3 has to go from tau 2 to tau 3. And of course, since there are 3 instantons in this particular example, there's this factor e to the minus 3 s1 over h bar. How do you do this integral? Well, anyone can do this. You can do the first integral. That leaves you with only 2 integrals to do. Do the second one. And finally, you do the third one. So you get t cubed over 3 factorial and this thing as before. You can generalize this to n instantons, and you get t to the n over n factorial times this. Okay, and I'm now able to give you the complete amplitude to go from minus a to plus a through any number of instantons. It can be 1 instanton plus 2 instantons plus 3. Sorry, I said this wrong. 1 instanton or 3 instantons or 5, 7, etc. Why? Because, see, I have to go from here to here. And so it has to be an odd number of instantons. So I must sum over n odd. This everyone recognizes is the expansion, is the Taylor series for hyperbolic sine. So this I get over here. What about solutions that return back to minus a? So you see the particle on the hill goes to the other side, comes back, that's 2 instantons, goes back again, comes again, it's 4 instantons, 6, 8, 10, 12. In that case, you will sum over n even and you will get cosh. So we are at the end of this lecture. We've calculated the amplitude to go from minus a to plus a, left to right, got that as sine. Left to left, got that as cosh. In terms of the single instanton action, starting at minus 2, minus t by 2 and ending at plus t by 2. Having said all that, I have done a big mistake. And what I've told you is wrong. I did so deliberately to simplify things. And I'll tell you where I have been telling you lies. It's at let's see. Yes. Here is where I have been telling you lies. Where I said you have to take the instanton at every time, add up all of them. And that is actually not so bad a lie. But there's a factor that is missed out over here, which I'm going to clear the next time. So instead of trying to confuse you, instead of trying to bring in too much detail, I simply said that I'll take all positions of instantons, which we will again the next time, but it has to be done very delicately because we are expanding in a complete set phi n. And what we have found is that phi 0 is what we will see next time is that phi 0 is a zero eigenvalue. So in fact, we need to calculate a determinant in which the lowest eigenvalue has to be removed. It's a delicate matter, but the entire physics will be unchanged from what I have told you today. So in conclusion, the next time, so next week when we have our lecture, the only difference that will happen is that this P will be replaced by a factor which I'll call K times T. So there'll be KT over here and KT over here. It will look very much the same, but there's a lot more work that has to be done in order to get this right. For those who want to read more about this, there are a number of very good books and review articles. So there's this one which I would highly recommend, and this is our textbook anyway. And Advanced Topics in Quantum Field Theory by Schiffman. This is really one of the most important works in the field. Okay, so that's all for today, and let's see if there are questions.
All right. So one thing I noted earlier was that your amplitude terms, they seem to resemble what you had in the previous lecture, but with sines replaced with hyperbolic sines, cosines replaced with hyperbolic cosines, so essentially Wick rotations of one another. Once you have the amplitude here at the end of this lecture, can we Wick rotate it back to get something in the case of real time?
Yes. So if you calculate something in imaginary time, and that calculation is easier to do than in real time, the question is, can you go back to real time? The answer is yes. Sometimes there are subtleties, but usually if there are no pathologies, then the answer is yes. So always the better thing to do is to first go to imaginary time and then go back, or as he says, Wick rotate back to real time.
Could you explain your graphs for the instant?
Why some have a longer time period, like the time between them, some have shorter, like the end slides, like the graphs or the instantons. Why, like there's wide.
This is a one instanton graph. Well, it's a plot of the particle's position as a function of time, imaginary time, of course, tau. So it starts way back in the past at minus a, and then way into the future, it's at plus a. It never comes back. However, here it goes to plus a, and then an anti-instanton, which means that it'll start at plus a and then end at minus a. It takes it back to minus a and then up and back. So 3 times the axis has been crossed, here, here, and here. So these are 3 instantons. It's not that one instanton has gotten fat. No, these are like 3 kinks, almost zero width instantons.
But I mean, like for example, from 3 to 5, like the gap from when the first instanton appears in the second instanton, it's a fatter gap, and then compared to when there's 5 instantons, the first to the second is smaller gap, and the second to third is a wider gap and shorter.
Yeah, absolutely. These are completely random. So here, let me show integral. So the only requirement is that tau 2 be bigger than tau 1, tau 3 be bigger than tau 2. So in other words, tau 2 can take any space in between these. Tau 3 can take any space in between these. And so everything is possible. So it can be that instanton number 1 is now, and instanton number 2 comes after 10 years. Or it could come after 10 microseconds. So it's completely random. You have to take all possibilities into account.
Okay, so are these instantons related to topological defects? Because there is a Z2 symmetry in this double well potential. If it is broken, then domain walls will be produced. So is there a connection between these two?
Oh, yes, of course. You see, the instantons that I've talked about are the very simplest. They are those in quantum mechanics. It is from this idea that topological instantons was developed. Now, in a topological instanton, you have the same situation. That is, you have a vacuum here and a vacuum here. Those vacua are degenerate with each other. Now, they can be degenerate for any reason, and the reason could be topology. So, in gauge theories, you can do a large gauge transformation, and you can have an infinite number of vacua, which are different from each other because they are labeled by some different topological quantum number. And then there can be tunneling between those different vacua.
Hi there. My question was that, as you said, that overlapping instantons are hard to calculate, right? Could I assume that overlapping instantons would have like both of the kinks exactly at the same point? If
Okay.
according to this graph.
Okay, so let me go to a nicer graph, okay? Let me go here. So here I have something that goes up. Now, what if there was an instanton that was the anti-instanton that took it down over there? It's far enough away, doesn't matter. But what if there was one that there was overlapping? Well, that would then not be a solution of this equation. And people have looked for exact solutions of this equation,
Right.
which are different from this, but they haven't found any. Maybe there are not any. And
But couldn't you try to put a limit on the value of tau that it reaches 0 and then like go up and down at the same time? Kind of exactly the
I
same.
remind you of the situation.
Right.
There is this particle on the hill at minus t over 2. there's this particle on the hill at time plus, it has to make its way to this position at time plus t over 2. Okay? And the solution of the classical equations, Newton's law, is the solitron. Now, the only solution that we know is this tan of omega t over 2. Maybe there are others, but nobody has succeeded in finding them, because you see, this is a nonlinear differential equation, and nonlinear differential equations, there are no theorems which say that this has got one solution or has got 500 solutions. But nobody has been able to find that. At least that's my understanding. Okay, so I think we are done. Thank you.